Let's continue with the second law, or it's more commonly known as the law of the entropy. Now, before writing the second law, we should first define what entropy is. Now, let's look at a special engine, so-called the Carnot engine. Now, in fact, before studying the Carnot engine, let's look at this work. We have the piston with some gas filled. We said that the work done by the gas is PdV. If the gas is compressed, dV will be negative. The work done by the gas will be negative. Well, that is basically because we are doing work on the gas, so the energy, internal energy is increasing. The gas is doing negative work. If the system, the piston is expanding, then dV will be positive, and since the gas is pushing the piston away, and so the work done by the system will be positive. Now, this thermodynamic studies started mainly because of the interest in heat engines. We don't always have ideal systems in equilibrium. Let's say that we compress this gas very fast, so that the system is no longer in equilibrium. Then what can we say about the work done by the gas? What can we say about this? It's no longer in equilibrium. So initially, let's say it's in equilibrium, so we can talk about the initial pressure of the system, but we cannot talk about the pressure of the system afterwards. Now, in order to calculate the work done by the gas, let's look at the work done by you. You are basically pushing it very fast, much larger than pressure times the area. So basically, you will be creating a shock wave, and the pressure at this layer will increase. So you see, Newton's third law always holds. If you want to exert a large force, the system should resist you with a larger force. You cannot just exert a large force if the system doesn't resist you. So at the moment that you push, basically at this layer, you are increasing the pressure. The rest of the system doesn't feel it yet until that sound wave reaches there. So the work you do will be the first force that you exert times the displacement. Well, the force that you exert will be larger than or equal to pressure times the area times dx. This P is the pressure just before you exerted the force. Since you are exerting a larger force, the work that you do is larger than P times A times dx, or P dV. Well, the work that you do is still minus the work done by the gas. So the work done by our system will be less than or equal to, here there is a minus sign. You see, dV is the change in the volume of the gas. Since I'm compressing the gas, dV is negative. So minus dW is larger than or equal to minus PdV. The work done by the gas is less than or equal to PdV. Yes, most of the time when we are talking about thermodynamic laws, that's applicable to all systems, not necessarily systems in equilibrium, we will be talking about such inequalities. So this is an inequality, and the equality holds if the process is a process in which we have, throughout the process, if we have mechanical equilibrium, the equality holds, otherwise the equality doesn't hold. Now let's go to the Carnot engine. It's a very simple 4-stage heat engine. So we have two heat reservoirs, one at temperature T1, the other at temperature T2. This is what we would like to do is we would like to construct a machine that will do some work. So let's see. Initially, here is our piston. We would like it to do work, so it is expanding. It is doing some work. Then we isolate it. This is isothermal. It's at constant temperature. Then we isolate it. We are moving it to the colder reservoir. We let it expand even further. It is being cooled down. Once it is at the same temperature of the second reservoir, T2, we put it in contact with the second reservoir. Yes, if you imagine an engine, you would like to run it repeatedly. So we are kind of trying to complete a cycle. We started from some initial macro state. At the end of this cycle, we would like to go back to the same macro state. Now, why did we make sure that it got, before putting it in contact with the colder reservoir, so we made sure that our system came back to the colder temperature, is mainly because of the second law, which we will state in a moment. But let's just imagine this is what we are doing. So we have, initially, my engine is in contact with a hot reservoir. It's expanding. It is doing work. Is it delta U is delta Q minus delta W. It is isothermal, so delta U is 0. It is expanding, so the gas is doing work. Delta W is positive. And delta Q also has to be positive. Delta Q has to be equal to delta W. So my heat engine is taking heat from the hot reservoir. At the second stage, it's an adiabatic process. Delta Q is 0. It is still expanding, so it is doing work. So delta U is negative. It's converting some of its internal energy into useful work. Now, my gas had expanded. I would like to bring it back to the initial state. I would like to compress it. So I first bring it in contact with the colder reservoir and compress it. So since the temperature is fixed, delta U is 0, I am doing work on the gas. So the work done by the gas is negative. Let me call this omega 1 and this Q1. Delta W is negative, so let me call that minus omega 2. Basically, I mean, you see, in the first stage, first two stages, I took some work from, some energy from my system. Now I'm giving some of it back, basically. And delta Q is equal to delta W, and hence it is also negative. So let me call this minus Q2. And then I compress it by some amount, and in the fourth stage, I separate it from the, isolate it from the cold reservoir. I keep compressing so that it's heating up until it will reach the temperature of the initial reservoir. So here, it's isolated, delta Q is 0. The work done is still negative. And the change in the internal energy is also is positive. Sorry, it's positive. Okay, now if I would like to show this in a PV diagram, You see, I started with a small volume. Small volume, large pressure, large temperature. Small volume, let me call this V1, P1. I started here. I first expanded it isothermally, so that is PV is constant up to some point. And then in the second stage, I expanded it adiabatically. PV to the gamma is constant. And remember, gamma is larger than 1. So pressure drops faster in an adiabatic process, faster than in an isothermal process. So that's why it just doesn't follow the same curve. And then in the third stage, I start compressing it isothermally. Again, PV is constant. And then finally, I compress it adiabatically. It reaches the initial point. So once it comes to this point, let me call that point A. At the point A, the pressure is the same, the temperature is the same, the volume is the same as in the beginning. So I can just repeat this cycle and extract work. The work done is, remember, the work done is the integral of PdV. Basically, it's the area under this line. Now, in this case, the total work done is, the net work done is that area. During this, as it goes from A to B, it took energy from the hot reservoir. As it goes from C to D, it just dumped some of this energy to the colder reservoir. So any questions up to here about this cycle? Now let me also give some names. So let me call this V2, P2, V3, P3, V4, P4. Well, A and B are on the same isothermal curve, which basically tells me that P1 V1 is equal to P2 V2. Similarly, C and D are on the same isothermal curve. So P3 V3 is equal to P4 V4. Now, A and D are on the same isothermal curve. In the same adiabatic curve, which basically tells me that, let me use the temperature. You see, T times V to the gamma minus 1 was constant. So T1, you see, the hotter reservoir is T1. This is at T1. This is at T2. T1 times V1 to the gamma minus 1 is equal to T2 times V4 to the gamma minus 1. And, no, this is, yes. And since B and C are on the same adiabatic curve, the temperature of B is T1, its volume is V2 to the gamma minus 1 is equal to T2 times V3 to the gamma minus 1. So basically from this, you can find the relation between V1, V2, V3, and V4. They cannot be just arbitrary four volumes. They have to be related by V1 over V2 should be equal to V4 over V3. Now, you see here, we did an example of how to calculate the work done. So that is one of your homework. Work done as you go from A to B. Work done as you go from B to C. Work done as you go from C to D. And the work done as you go from D to A. We know the equations, how pressure and volume are related to each other during all these processes. So you can just take the PV integral. Well, you know the temperatures. Well, we had already written over there that in certain stages delta Q is 0, in certain stages delta U is 0. So what is Q1? What is Q2? You already know delta U as you go from A to B, delta U as you go from B to C, delta U as you go from C to D, and delta U as you go from D to A. Now, one thing you will see once you calculate all these is that Q1 over Q2 is equal to T1 over T2. Well, the work done by the system, well, energy conservation tells me that this is Q1 minus Q2. We are usually interested in what's called the efficiency, is how much work could you extract per energy you had given to the system. Well, the energy we had given to the system is Q1. So this is 1 minus Q1 minus Q2 over Q1, or 1 minus Q2 over Q1, which is 1 minus T2 over T1, which is less than 0. Oh, sorry, less than 1. You cannot have a machine that is 100% efficient unless you reach 0 Kelvin.
Is matter-antimatter collision 100% efficient?
How do you see, for example, a refrigerator, the efficiency of a refrigerator is more than 100%. Or not, sorry.
No.
Yeah.
It's not more than a real refrigerator.
How do you define the efficiency? That's the crucial thing. No, not the refrigerator, the heating.
Yeah,
Heating by using an air conditioner. You do some work. What the air conditioner does is it takes heat from the outside and puts it inside using the work that you had done. So the heat that it dumps in your room is larger than the work that you had given to the system. So in that case the efficiency is larger than 100%. So that's the definition of efficiency. How do you define, what kind of efficiency would you like to talk about when you are talking about particle-antiparticle annihilation? This is about heat engines.
There's no matter-antimatter annihilation that results in just photons, for example. There's no wasted energy, right? There's no...
Yeah, you see, in particle physics, the only energy you have is the energy that your particles have. There's no other energy. So you cannot talk about wasted energy. They are all in particles.
Wasted energy is heat, right, in microscopic systems, which is the average kinetic energy of microscopic systems.
Which you cannot define for systems with small degrees of freedom.
You can define kinetic energy.
Yeah.
So particle collision where the resulting thing is zero kinetic energy is so you can't have zero kinetic energy. So it's preserved there from the uncertainty will stop.
Anyway, we can discuss it later. Okay, there is a point I would like to make before. Okay, I don't know if there is another lecture. Okay, so this is the efficiency. But what I would like to concentrate on is this one. Q1 over Q2 is equal to T1 over T2. Let me write it in a slightly different form. This is for a Carnot engine. Q1 over T1 is equal to Q2 over T2, or Q1 over T1 minus Q2 over T2 is equal to 0. So this is the form I would like to write it down. Now let me draw the Carnot cycle once more. Q1 is the heat taken during that process. Q2 is the heat given out during the other isothermal compression. Let me look at this integral throughout this Carnot cycle. Well, how do we understand this integral? Just I have this closed loop divided into very small parts. And calculate dq by t for each one of those parts and sum them up. That's the definition of the integral. So I can divide this into from a to b dq by t, from b to c dq by t, from c to d dq by t, and from d to a dq by t. Now, as I go from B to C, well, it's an adiabatic process. There's no heat exchange. So dq is 0 during that process. This is 0. As I go from D to A, well, the same thing. It's an adiabatic process. So there's no heat exchange. This is 0. As I go from A to B, it's an isothermal process. So temperature is constant. It's T1. As I go from C to D, again, temperature is constant, it is T2. Remember, dq is the heat given to my system during that very small step, during my process. Now, as I go from A to B, if I just sum all the heats given to my system, that is nothing but Q1. Now, as I go from C to D, my system gives away heat Q2, but that is the same as minus Q2 given to my system. So it is minus Q2 over T2. But remember this relationship. That relationship for this Carnot engine tells me that this is nothing but 0. So dq by t, well, this we had derived for a particular system, but you can actually go ahead and prove that this is valid for any system that is always in equilibrium. This is always 0 if the process is reversible. Well, if the system is always in equilibrium, it is reversible. So does this equation remind you of anything from mechanics? It's a conservative force, so if you have a conservative force, you can define a potential. Basically, this tells me that if I have an initial point and a final point, as long as I move along a reversible process, the integral dq by t from A to B is independent of path, as long as I'm moving on a reversible process. But that means that this integral can be written as the difference of a state function. And that state function is what we call the entropy. So the S, so this is SB minus SA is defined to be this integral. And again, I repeat that if you want to calculate the difference in the entropy between two macrostates of my system, what you need to do is you have to find the reversible path connecting point A to point B and integrate dq over t along that path. Which path? Well, it doesn't matter. As long as it's a reversible path, all the answers, all the results will give you all the paths will give you the same answer because of this result we have over here. Now the statement of the second law is that, well, you see, this is for a reversible process. For an arbitrary process, this integral is less than or equal to 0. Now this, okay, we will continue on Wednesday. This will tell us that the entropy of a closed system either increases or stays the same. That this basically will tell us the increase of the entropy. But we will pick it up from here on Wednesday. Now for your homework, you will have at least 1 week to do them. So I will probably have more questions for you, along with this one. But you will still have 1 week to complete your homework assignment.
We have 2 weeks right now, right? You won't be here next week, right? So
I mean, the homework, we will upload them in up to class.
No, but I mean, can we have 2 weeks for the first one, if you're not going to be here anyway?
We will see. Depends on the homework. Come on, you should solve this problem tonight.
But other thermal stuff.
Any questions? Any last questions before we leave?
I don't understand when should we solve
No, you see, when the homework is due.
Yeah.
Now, this will come,
Okay.
but when we distribute the homework, you will have the due date. You will have at least 1 week
Okay.
after we announce the homework officially.
Will this be written in the homework?
Yes, this will be written in the homework. Don't worry. And for those who are not in OT class, just send me an email so I can add you to OT class.